In this lecture, we'll see how we can build cutting edge text to image generation models like Midjourney, like Dall E3, like Stable Diffusion. So these three are the big three architectures which are based on similar thing, and they generate take text as an input and generate the output. So depending on the domain of the company you work in, you could build either, let's say, crystalline structures or biodiversity images, or some images related to manufacturing, or images related to, let's say, pharma industry and the chemical molecules, or anything else. So the base model remains the same, base architecture remains the same, and then we refine and build it, make it more specialized for the domain we want. That is what is stable diffusion. So before we study stable diffusion, we need to understand something called as latent diffusion. Okay. So we have seen until now these diffusion models. What do diffusion models do? They take a image size of a noise, and from that noisy image, it removes the noise until we arrive at the image we want. So it's an incremental noise removal. So UNet as a model predicts the noise. So these are the few important things. Now, what is latent diffusion doing? To generate an image worth of 256 by 256 pixel, it takes around 30 seconds or 40 seconds just for 256 pixels. Imagine if you wanted to generate an image of 10 megapixels. And the thing is, model size grows in a square proportion to the image size required. So just think about the images right now. At minimum, we have 50 megapixel. And this is 256, only 256 pixel. It's not even zero point 0.2 megapixels. Okay. So you can imagine how difficult it is going to be to train and even produce the images from such a big models who we need to generate big images for. So we have a shortcut. The shortcut is there is a architecture which we call as encoder decoder architecture. Okay. It's just a name for it, and it's simple. It takes a big image and it compresses it into a smaller representation of that same image, such that decoder can uncompress it and we can get back the original image, or very close to the original image. So this way, a big image is converted into a smaller image. So now if you go to this code, if a 256 pixel image is converted into 50 pixel image, then using the same computational resources as this pipeline, we can generate 4 times more size image. Because if you can compress 256 to 50, it's like a 4 or 5 times compression. So if we take this pipeline and on top of this pipeline build this diffusion thing, we can generate even bigger images. And that's why latent diffusion model is there. What it does, it compresses the images, and all this diffusion process happens on that compressed representation. That compressed representation is called as latent space. Okay. So entire architecture remains the same. If you check the code, in the code, there is this UNet model, and we have seen multiple times until now. We say UNet model and we give the image to it, and we also give the timestamp, and that's it. It gives us predicted noise. For latent diffusion model, the thing changes to just this. Instead of image, we take latent image and timestamp remains the same. So code doesn't change much and nothing changes much. We just have an extra model, which is this encoder decoder model, which is called as VAE. So VAE dot encoder, we get, image is converted into latent. So VAE dot encoder converts image into latent image, and VAE dot decoder converts latent image into image. So this is how the latent diffusion is. Now, by combining this with stable diffusion, that's when the power is actually unlocked. And this slide, this unit 3, the final unit of diffusion course, it talks about these things. As the image size grows, computation power required grows, and we can easily compress that. So for example, 512 pixel image can be easily converted to a 64 pixel image, so a latent space. And here if you check in the code, the thing in green is the compressed latent space. That's why the model unit will be smaller, faster. If we didn't have this compressed space, if we operated in original image size, this would be a lot bigger, square of the image size. So encoder, decoder. And this is the our beginning of stable diffusion. So until now, we have also seen text conditioning. Okay, what did we see? We saw that if you want to change at runtime what kind of image is being generated, that is what we used guidance and conditioning for. Okay, stable diffusion goes a bit further. It for conditioning, we have already seen in the previous lecture, we use open source model by OpenAI called as Clip. Clip, it is a model generated to map words with image. Okay, it's not for image generation, it's more like matching the word description of an image with the image. So here in this, we use text conditioning to fine tune the kind of image we are generating. Or then there are other things. So for example, we could, instead of conditioning, just conditioning, I want image of this color, or I want an image similar to this text vector. We could also say, depending on the condition, you know what, I want image in depth map of this. So we have a control over where the face is looking. For example, I want face looking up like this. I just have to give that depth map, and the image model is going to generate it because conditioning. At inference time, we calculate the loss of this condition which we are giving and the noisy image which is being generated. And in the middle, we try to we then find this output we is in the direction we want. So this is introduction to stable diffusion. Internally, it is made up of these components. So if you go inside, the components are here. So stable diffusion contains these many components. Let's, in your mind, you should have a big picture view. Okay. First thing I mentioned that we don't operate on an image as is, we operate on a image compressor and decompressor. And I said it's a VAE. So this is image compressor and decompressor. Then we have a unit model, which is predicting the noise. So we have unit, this compressor and compressor, we give the model to unit. For diffusion model, we also have scheduler. Always we have the model and we have the scheduler. So these two, and then VIE, encoder, decoder. Now on top of this, okay, this is still just latent diffusion. This is still just latent diffusion. On top of this, if you add this clip model, okay, and I had asked this question on Hugging Face. It is a very interesting question. How is text conditioning different in latent diffusion and stable diffusion? The key point is in latent diffusion, we use the text conditioning at noise injection level. The model remains unchanged. Only at noise addition runtime, that's when the text information is used. And in stable diffusion, we train the model with the text embedding. So the information about the text goes inside the model. And that's why we have a much more fine-grained control over the output we get. So going back to this, we have something which takes in text, and that is the text encoder. And if you have done NLP course, you will know that every NLP pipeline has, just like images, diffusers. Diffuser has unit and scheduler. In similarly, transformer has the model and it has tokenizer. So we have text encoder and tokenizer. And clip is a model which connects text with images. Clip is a model which connects text with images. So that model not only has just text encoder and tokenizer, it also has image model which takes in an image, converts it into its features. Okay. So this is how these components are. Even though they are not logically related when you take a look at the output, but in your brain, conceptually, what do you have? You have a latent space. VAE model is that latent space thing. You have the diffusion pipeline, which is unit combined with scheduler. That's a regular diffusion pipeline. Then you also have clip. Clip model, it takes in text and image as an input, and it gives us the result of how same or different they are. So for text, we have tokenizer combined with encoder, and the image to the clip is feature extractor. So if you check here, it's all part of here in the code. So when you logically connect these things, this architecture of stable diffusion will become a lot easier. Unit model takes in the latents, like latent diffusion. It also takes in text embedding value. So until now, if you check in the code, until now we were taking either image or latent image and just timestamp. In stable diffusion, we also take text embedding. That's why we have fine-grained control, right? So unit is only doing that. We added this. We ensure the sizes are so that this addition and multiplication in this model happens, and done. We have, using these small 5-6 pieces, we have a model which is capable of taking our input as anything and generate a very interesting image out of it. So take a look at this image. Such an interesting image, a painting of a white flowy sheet ghost with two painted black oval vertical eyes in the library holding a black cat. Weird, right? I mean, it is able to generate that because in the model parameters, it has a lot of images which it has been trained with, and also their descriptions. Uh, It is trained on stable diffusion, is trained on stable diffusion is trained on billions of images. It's a some Leo something data set. I forgot its name, but we those many images, their description, and this model has been trained on those description. It takes huge computational power, but we don't need to train it from scratch because we directly have this available uh, as a ready-made thing to us, and that is what is stable diffusion pipeline. Internally, it is made up of these things I talked about. So this is how you can see, combining from latent, it is a very easy jump. Unit, encoder decoder, and text embedding and image extractor. So it's a very incremental growth from everything until now. Just small changes and we get a highly capable model. Now the problems here are because the model is such a capable that we run into problems like GPU memory is not enough. Google Colab doesn't have enough memory. So then you have to do these tips and tricks to compress the pipeline. And these are the advanced things of stable diffusion. But in the end, I do recommend you should be able to close your eyes and you should be able to tell all the components of a stable diffusion pipeline. VAE, what does it do? Then text encoder, what does it do? Feature extractor, what does it do? Where is it in? Who gives input to what? And when you can draw all of them, you have mastered stable diffusion. And the only thing which remains is how to optimize it for a use case. So this is just the start of the stable diffusion. Okay. And going further and how to fine tune it, it uses the same things as fine tuning until now. So we are now almost up to date with this state of the art image generation, except few optimization things. And this Hugging Face course goes through it very nicely. The only thing remaining is these extra sub features stable diffusion has. We will take a look at them in next lecture.